Hello, everyone. Welcome to the Invasive Mussel Collaborative webinar, Case Studies. Welcome to the Invasive Mussel Collaborative webinar, Influences of the Physical Properties of Water on Mussel Treatment. Thank you for joining us today. My name is Erica Jensen, and I'm with the Great Lakes Commission. And as I said, thank you for participating in our webinar today. For those of you who are not familiar with the Invasive Mussel Collaborative, the collaborative was convened in 2015 to identify opportunities to advance scientifically sound technology for management control of invasive dreissenid mussels in order to produce measurable ecological and economic benefits. If you'd like to know more about the Invasive Mussel Collaborative, we encourage you to visit our website at www.invasivemusselcollaborative.net. Today's webinar is part of an ongoing series hosted by the collaborative, and the purpose of the webinars is to facilitate learning and information sharing on topics of common interest within the invasive mussel community. It will be recorded and archived along with past and future webinars on the website. The focus of our webinar today is how physical properties of water may impact dreissenid mussel treatment approaches. And we are pleased to have speakers from the United Water Conservation District and the U.S. Geological Survey joining us to present recent research. While we always strive to minimize technological issues during these webinars, we apologize for any issues that may arise. And to help with this, I'm going to first cover a few logistical items before we get to the presentations. So those of you who are unfamiliar with using Skype, the audio for this webinar is automatically streamed through the computer speakers once you join the Skype webinar. If you would rather, you also have the option to change your audio to the telephone, and you can change your audio to a telephone line by selecting Switch Audio to My Phone from the banner at the bottom of the screen, and then by clicking Connect from the pop-up screen. A second pop-up screen will list the number to call into, as well as the conference ID number that will give you access to the webinar. If you are experiencing technical difficulties connecting, please send a message through the chat box located in the lower left-hand corner of the webinar window, and we'll do our best to assist you. When you're viewing the presentations today, if you would like to view them in a full screen format, you can change the screen layout to content view. To change the layout, select the layout icon in the upper right corner of your screen, indicated by the red circle shown on the slide, and choose presentation view or content view. In order to minimize the potential for interruptions and background noise, we have automatically muted all attendees' lines, and attendees will remain muted throughout the webinar. That being said, we do encourage and accept questions from attendees, and we accept them in written format. So if you have a question for any of our presenters, you may type it into the chat box that we showed you previously, signified by the chat bubble icon. Questions can be submitted this way at any time during the webinar, and depending on time, we may be able to answer one or two questions following each presentation, but we will likely hold the majority of the questions to the end of the webinar after all of our presenters have spoken, so that we make sure we have adequate time for all of the presentations. We will do our best to take all of your questions and comments during the webinar, and if you do need to leave before we get to your question, we encourage you to go back and review the recording, because we will still ask the question, so you'll be able to hear it asked and answered on the webinar recording that will be posted to the website within a day or two following this webinar. So that covers all of the logistical items I wanted to go over this morning, and so now we are ready to go to our presenters. Our first presenter this morning is Katherine Ayres. Katherine is an associate ecologist with the United Water Conservation District in Ventura County, California. She is the project manager for United's quagga mussel monitoring and control plan, and the lead for pilot testing treatment options to address the quagga mussel infestation in Lake Piru. Welcome, Katherine. You should be all set to have presentation privileges, and I believe we already tested your audio.
Yes, can you hear me?
Yes, we can hear you.
Thank you. Hello, I'm Katherine Ayres. Thank you for joining us today and letting me discuss our work here at United Water Conservation District in collaboration with IMC Consulting. First, I'll give you a quick summary of the background of United Water, the history of aquaga mussel infestation, and our specific challenges, the goal of the treatment study, and then take you through the methods, results, and discussion of that study.
Katherine, you are breaking up just a little bit or fading in and out, so I don't know if you can adjust your microphone a little bit closer.
Is this better?
Yes, that's great.
Okay, I'll just move closer because I can't adjust it. Thank you. So the United Water Conservation District is a small water district in California that owns and operates the Santa Felicia Dam, which impounds Lake Piru, you can see on the map. United also owns and operates the Freeman Diversion, which is used to divert surface water and circulate the water into the ground to recharge aquifers in Ventura County. United uses Lake Piru as a reservoir to store water during the wet season. And then during the dry season, we usually release water to Piru Creek. I'm not using that. Is it not working?
Katherine, I apologize. You're still fading in and out. Is there a connection cord?
I'm using the microphone on the computer, which is what we tested before.
Now I can hear you again.
Well, I don't think it's just the volume of my voice, or is it actually cutting out?
It's coming in and then fading out and coming in and fading out, so it's just not a consistent volume. If you want to try calling in on the phone, we can do that, and we can switch to our next presenter while we make that change.
Okay.
If you're able to do that, that might be best.
Okay, I'll call in.
Stephanie will put in the number to call in the chat window to make sure you have the right connection. I apologize. Thank you.
No worries.
All right. I apologize to our attendees that we have to make this change, but hopefully in the interim we can switch to our next presenter while we wait for Katherine to dial back in. So we will try again. Jim Luoma, are you with us and able to give your presentation now?
Yes, can you hear me okay?
Yes, loud and clear. Thank you. So just quickly, Jim Luoma is with the U.S. Geological Survey. He has worked for the Department of Interior in various roles, including fish propagation and aquatic research for over 27 years. Since 2010, he has been leading a group of USGS researchers at the Upper Midwest Sciences Center in La Crosse, Wisconsin, to develop and evaluate control tools for dreissenid mussels. So Jim, with that, we will try this again and hand off presentation control to you.
Okay, thank you. Let's see. There, I think, am I active now?
Yes. Yes, you are.
Okay, it's taking a little bit. Okay, so today I'm going to talk to folks about a study that we did to evaluate the effects of temperature and exposure duration on some toxicants that had potential for use as a rapid response control tool to eradicate them in rather limited situations, not necessarily whole lake treatments. First, I'd like to acknowledge the funding support for this project, which the bulk of the funds were from Minnesota Legacy Funds, administered via a grant through the Minnesota Aquatic Invasive Species Research Center. Substantial funding was also provided by the Minnehaha Creek Watershed District, as well as the EPA's Great Lake Restoration Initiative. And although I have confidence in the data I'm going to present, it still has not received final USGS approval, so it's preliminary in nature and subject to change. A little bit of overview about what I'll talk about is the need for the study, kind of our design concept, some information on a molluscicides that we evaluated, the test system and the methods we used, and then into the results and some considerations if a treatment was going to be done using some of these compounds. So we're all familiar with these graphs where it shows the invasion over time. The last 30 years, of course, zebra mussels have expanded their range throughout the U.S. and, of course, now are threatening waters in the western part of the U.S. As part of that response to the invasion into inland waters, Minnesota, Department of Natural Resources, and other local governments have been fairly aggressive in their efforts to monitor zebra mussel populations and then to respond with an early detection and rapid response treatment when they think they have a localized infestation. This is a list of some of those treatments that they have done, the various products that they've used over time. Although long-term success has been difficult to achieve, they haven't thrown in the towel yet. However, some questions started to rise when they're doing these treatments as what type of molluscicides can they use that would be effective in these treatments, what dose of the molluscicides is needed to obtain 100% mortality because they're trying to do an eradication, not just a control treatment. And then because a lot of these infestations tend to be discovered in the fall of the year when people are removing docks, boat lifts, and boats, the water temperature is decreasing, so they wanted to know what impact does a water temperature have on molluscicide toxicity. So with that knowledge, we developed this study concept to look at seasonal water temperatures, 4 temperatures, starting in September of the year and going through November. So when temperatures hit 22 degrees, 17, 12, and 7 degrees centigrade, we went out and collected those animals, so their seasonal effect and also temperature impacts, and then we conducted at those temperatures. Exposure durations range from 8 hours to 336 hours, which is 14 days. There are static exposures and static renewals for some of those tests in a controlled environment. And then we wanted to synthesize that into temperature-specific treatments. So the molluscicides that we chose to evaluate were 2 EPA-registered products, EarthTech QZ, which is a copper-based product, and Zequinox, which is a killed cell bacterium-based biopesticide. Both of those have been registered since about 2014, around there, for use in open water environments. Then we also wanted to evaluate 2 non-EPA registered products that have known molluscicidal activity, those being niclosamide and potassium chloride. Niclosamide is the active ingredient for balicide, which is various forms are registered with the EPA for use for controlling sea lamprey larvae. It's also used throughout the world in tropical areas to control schistosomiasis, and has been used in Minnesota, Wisconsin, and Michigan in the past to control the snail vectors that carry swimmer's itch. Potassium chloride. Potassium has been known to be toxic to zebra mussels since the early 1990s. It has been applied typically as a potash in a few different rapid response treatments, the most notable being the successful eradication of 5-hectare quarry lake that's hydrologically isolated in 2006. The test system that we used, again, was a climate-controlled environmental chambers, so we brought those animals in. Those chambers have a heated and chilled water supply. The picture on the lower left corner shows our holding tank. Right after we acquired those animals, we held them in that tank. After the exposure, we held them on the small tanks in the lower right. They were flowing through tanks. They were all fed during those times. This reed mariculture, instant algae, the upper left portion, you can see a batch of that food that was continuously supplied to those animals. The exposures were conducted in a series of jars that you see in the upper right of that photograph. A little more on exposures. They were 3-liter static exposures. The durations varied a little bit depending on the product. Zequinox, the activity biodegrades quite rapidly after hydration. It's virtually inactive after 24 hours after hydration, so we limited those exposures to 8, 12, and 24 hours in duration. The remaining products we evaluated for 24, 96, and then the 336 hours. They were single-time static exposures with the exception of the 336 hours exposures. They had static renewals every 96 hours. We did 5 concentrations of each chemical at each temperature with 4 replicates for each concentration. And each test jar, there was 20 animals in a jar. We evaluated, we held the animals after exposure to make sure that the products, particularly Zequinox, which takes some time for it to become toxic to the animals after it's ingested, and potassium tends to narcotize animals, so you might get some false mortality readings if you looked at them right away. So we held them for a period of time, which was standardized based on water temperature. What we did is assign 1 daily temperature unit for every degree Celsius for 24 hours. So our holding, post-exposure holding range from 10 days at 22 degrees to 31 days at 7 degrees, but the temperature units were fairly consistent. Throughout the exposure, we took daily water chemistry readings on each jar or post-exposure holding tank. Those included dissolved oxygen, pH, and temperature. We evaluated the alkalinity, hardness, and conductivity on the source water prior to exposures. And then we looked at total ammonia nitrogen at the termination of the exposures in negative and positive control test chambers. The concentrations were analytically verified by various methods. Zequinox concentrations were verified using UV vis spectroscopy. The closamide concentrations were verified using a liquid chromatograph MS. And then EarthTech and potassium chloride concentrations were verified by their respective elements, copper and potassium, by microwave plasma atomic emission spectroscopy. Getting into the results for the water chemistry as far as dissolved oxygen, pH, and temperature all remained acceptable above the criteria limits for aquaculture, as did the ammonia nitrogen concentrations in the untreated control test chambers. We did see some elevated nitrogen concentrations in the highest Equinox concentrations at 22 degrees. Getting into the results by chemical, there's a lot of information on this graph. It shows the temperature over on the left and broken out by exposure duration. The LC50 and LC99s, which are the concentrations predicted to produce 50% and 99% mortality of the animals, those were calculated based off of regressions created for each temperature and exposure duration. The take-home message is in the yellow here. This is the concentration of test article that either induced 100% mortality, or in a case where there's a greater than symbol, it produced at least 90% mortality, and that's the highest concentration that was evaluated. So as you can see with EarthTech, of course, the exposure concentrations, the amount of chemical required decreased over as you lengthen the exposure period, and as temperature increased, you can see. The trend was generally less material was required, except for this one at 22 degrees where it increased again. We attribute this to a couple of different things that happened during these exposures. The first being these tests were conducted in 2016. 22 degrees was our first test that we evaluated and conducted. We had some initial problems with that test that were subsequently corrected in the 17, 12, and 7 degree tests. Therefore, we repeated the exposures in 2017, which is the data that is shown here. When we went back to our original source of animals, which was Lake Minnetonka, there's a die-off going on in 2017. So we switched lakes. It was a different source of animals in a different year. So by and large, we attribute the differences in sensitivity to yearly and population variances. So there is some variance that we suspect between populations. So all of this data should be, carefully interpreted when used. Niclosamide is a product that is quite toxic to zebra mussels, and we can achieve virtually 100% mortality at any exposure duration and temperature tested, although we missed it by a few animals here and there. They all achieved over 90% mortality. The concentrations in red are actually nominal concentrations. We had a malfunction of our LC at that time, so those are nominal concentrations that are reported. Potassium chloride is a product that was highly influenced by temperature and exposure duration. 24 hours practical concentrations are not really achievable to get 100% mortality. At 7 degrees, although we achieved over 90% mortality, it's very high concentrations. You only really get to reasonable concentrations for field applications with 336-hour exposures at water temperatures 12 and greater. And at our warmest temperature, 96-hour exposures appear to be adequate for achieving 100% mortality. Zequinox, while a product that has some definite benefits as far as selectivity towards dreissenid mussels and probably a good management tool product as far as eradication, we did not achieve consistent 100% mortality in any of these replicates, so we pretty much ruled it out as a solid candidate for use in early detection rapid response treatments for zebra mussels. So this is, kind of condenses the data of the three chemicals that we look at as potential eradication tools. Again, EarthTech, 24-hour exposures, not all that good for doing those treatments. It takes a lot of chemical, and we never achieved 100% mortality on them. The 336-hour exposures are all below the labeled concentration, which is 1 part per million as copper, including background copper. That equates to about 20 milligrams per liter weight to volume. So even at 96 hours, we're very close to probably to achieving 100% mortality at temperatures above 12 degrees. Niclosamide, we can achieve 100% mortality, as I discussed earlier. However, there's probably a significant non-target mortality in those treatments. Potassium chloride, again, not a good cold water temperature chemical. However, when the temperature warms, particularly long treatments at 12 degrees or warmer, and 96-hour treatments at 22 degrees and warmer probably would be effective. Here's some comparative data from some work that was done in the early 90s. This is important to water chemistry. This was soft water, so some of this you have to take with a little grain of salt. Balicide, which again is the salt formulation of niclosamide, does show some selectivity towards zebra mussels. These are LC50s, not LC100s. However, there does seem to be a little margin of safety there, although there would be some definite impact to fish. Potassium chloride, again, quite a window of opportunity there as far as being able to safely treat, especially at a concentration that a longer duration exposure would be effective at. Copper here, now this is copper sulfate, not earth tech, and again, in soft water, so these numbers you have to take with a little bit of grain of salt as far as the concentration. But for example, Minnesota has done some treatments at a 0.5 part per million of copper, which would be 10 parts per million of earth tech, up to 1 part or 20 parts of earth tech, with minimal non-target animal as far as fish toxicity goes. Probably all of these products, of course, would kill any native unionids in the treatment area. So for final consideration, if you're going to use these products for an early detection, rapid response treatment, we need to know the knowledge of the extent of the infestation. So basically, is a treatment worthwhile? If we know that the animals are contained and can have high confidence of that, then the treatment probably is worth taking on. If not, then obviously it wouldn't be. Another consideration is that our study was performed in a laboratory environment with well water, natural waters that have an algae load and sediments that can sequester some of those products. That should be taken into consideration as well. Water temperature, as we have shown with our data, and water chemistry impacts the toxicity of these products. As the water temperature is warmer, the available molluscicides increase and the toxicity of those products increase, so you can probably have more effective and more cost-effective treatment at a warmer temperature. Salinity has been shown to impact the toxicity of potassium chloride. So if you're in a region of the United States where salinity is a factor, then that should be considered in your treatment molluscicide selection. And alkalinity and hardness, if you're in soft waters, that has been shown to increase the non-target toxicity of copper. Collateral damage, of course, as far as native mussels, are there endangered species in that area that you should be concerned with? Potential for fish kills. The ability to maintain an effective dose, obviously, is a consideration. None of these chemicals are very acutely toxic. You need to maintain a concentration for an extended period of time, so if that's not feasible, then the treatment's probably not going to be effective. Of course, permitting requirements. The earth tech is registered with the EPA for use, probably require less local and state permitting than a product like nicosamide or potassium chloride would require. So urgency of treatment would come into play there. And we recommend the use of either on-site flow-through or in situ bioassays to make sure that your concentrations are really achieving the mortality that you're trying to achieve. So if we have time, I guess I'll answer a few questions. Otherwise, we can hold them till the end.
Thanks, Jim. I think people are still processing all of that information that you provided, so we don't have any questions yet, but we will keep tabs to see if any come in. And then I think with that, we will go back to Katherine. I think she is reconnected via our audio, and I apologize, Katherine, that we had that trouble, but hopefully this will work better for us. And if you're on the phone, Katherine, you can hit *6 to unmute yourself.
Okay, did I unmute myself?
You sound great. Yes, you did.
Is that better?
That's great. Thank you.
Okay, so I actually think that talk provided a lot more background than I have, so I think it worked well, actually, to go after Jim. So where were we? All right, So the United Water Conservation District is a small water district in California that owns and operates the Santa Felicia Dam, which impounds Lake Piru. United also owns and operates the Freeman Diversion, which is used to divert surface water and percolate the water into the ground to recharge aquifers in Ventura County. United uses Lake Piru as a reservoir to store water during the wet season, and then during the dry season, we usually release water when there's not a drought to Piru Creek, which flows to the Santa Clara River, where we then divert the water at the Freeman Diversion for groundwater recharge. The Santa Clara River is a relatively natural river that has escaped most of the channelizing and urban development seen in most LA area rivers. So it's a targeted watershed for recovering the endangered Southern California steelhead population. So that comes into play in a minute. Oh, I have to take over. Hold on a second. All right. Okay. Are we on the slide history of quagga mussel infestation? So quagga mussels were first detected in Lake Piru in December 2013. The infestation was in full force by 2016, with mussels recruiting on pretty much every substrate in the lake, including the soft sediment on the bottom of the lake, where mussels would attach to debris, trash, Asian clams, and other mussels, and they would expand from there. In California, a water district or other entity that manages dreissenid-infested waters is required to develop and implement a monitoring and control plan under state law. It must include a strategy for control and eradication, or eradication, of both adults and villagers. United has struggled with this plan because we're also subject to federal law under the Endangered Species Act and our Federal Energy Regulatory Commission license, or our FERC license. It requires United to release water year-round to meet habitat requirements for the federally listed steelhead. Because of the required water releases and consultation process for endangered populations, coming up with an eradication plan has been more challenging than it would have been if we could just stop our releases, isolate the lake for treatment, and dry out the creek below the dam, where the mussels have also spread. So when Jim mentioned collateral damage, we're very concerned with that in our system. So when looking at previous eradication attempts, it seems that potassium chloride and copper come up a lot, and so you just heard some about these products and chemicals. Potassium was a successful agent for eradication at Millbrook Quarry. Another apparently unsuccessful eradication attempt occurred with copper sulfate at Offutt Air Force Base, which resulted in a significant fish die-off. So at the bottom, it was about 40,000 pounds of dead fish, which would be concerning given our situation with steelhead critical habitat. Therefore, we're looking for an option that would be cost-effective and practical while minimizing toxicity to fish, particularly trout and steelhead. So another thing to note is the conductivity of the water in these two eradication attempts. So it's pretty low compared to our system, which I'll get into. So, however, water chemistry, especially the presence of high concentration ions, can play a substantial role in the toxicity of these compounds, like Jim mentioned. Unlike the Great Lakes or these sites on the table, Lake Piru has very high specific conductivity. Some prior work indicated that successful use of potash in high conductivity systems may require substantially higher application rates. In addition, even at its minimum pool, Lake Piru is a much larger body of water than Millbrook Quarry, as you can see in the table, or the lake at the airbase. And the amount of either product would be significant, with consequences for both the cost of treatment and the likelihood of undesired environmental effects. Therefore, we set out to address the following goal and trying to figure out what we want to do. We want to identify the optimal molluscicide product and concentration that will effectively control or eradicate quagga mussels in Lake Piru while minimizing adverse effects to non-target species, particularly trout and steelhead. So similar, but a little different than the last talk. We tested 4 different potential molluscicides. In the interest of time, I'm going to focus on the first 2, Earth-Tech QZ, which you heard about a minute ago, which is a formulation of chelated copper sulfate pentahydrate, which is different from the formulation of copper sulfate that was used at the airbase. And we also tested potassium chloride. These are the 2 options we identified as feasible for a lake-wide or other large-scale treatment strategy. The general approach of our study was also static testing to test a range of potential concentrations with the intention that the values would bracket the maximum reasonable application rate, as well as identify the lowest usable concentration. From prior work, we know that there is potential relationship between water temperature, as you heard a second ago, and toxicity. To ensure that we will be able to design successful application approaches, we applied these chemical concentrations over the range of temperatures that our lake experiences. So basically the idea is that the same concentration of chemical may result in complete mortality at high temperatures, but not at low temperatures. So we would only have a reasonable application in warm conditions. So we wanted to make sure we knew what those were. Also, previous studies show that potassium is less effective in high conductivity water. So again, given that Lake Piru averages about 1,000 microsiemens per centimeter and can get up to almost 1,600, we've been pretty skeptical that potassium would truly be a feasible option for us. It might not be effective, but we decided we needed to test the hypothesis, especially for our stakeholders and for processes that require looking at alternative approaches. So we tested 3 concentrations of each chemical at 3 different temperatures, shown here. We used static bioboxes of 10 liters of water and water straight from Lake Piru. All combinations of concentrations and temperatures were run with 4 replicates, so 4 different coolers or bioboxes, and 100 animals were used in each biobox for a total of 400 animals per treatment, and biomass was kept roughly equivalent between each set of 100 animals. Controls were also run with raw lake water. Animals treated with copper were counted whenever we conducted a check, so that was every day or every 3 days, depending on the temperature. Dead animals were counted and removed prior to replacing the bag of animals in the biobox. Animals treated with potassium were allowed to recover for about 48 to 72 hours, depending on the treatment. This involved letting the animals recover in fresh, raw lake water prior to counting. This was done because potassium can result in the animal gaping, even though it is not dead. So gaping is used to score an animal as dead. You can see the animal in the upper right corner of the slide. That's the gaping, kind of the one on the left is gaping. So therefore, the recovery step prevents animals from being mislabeled as dead, even if they're actually alive. So that's an important step if you're testing potassium. Here are the results for the animals treated with Earth-Tech QZ. And so the way I approach this is a little different than the last talk, in that I put parts per billion elemental copper versus the concentration of Earth-Tech QZ. So just to take you through this, the x-axis shows the days of treatment, and the y-axis shows the percent mortality. The columns show the low, medium, and high concentration of copper in parts per billion elemental copper. And the rows show the low, medium, and high temperatures tested. Red arrows show the treatments that resulted in 100% mortality, because that's what we're interested in, with the number of days to 100% mortality written under the arrows. The mortality curves clearly show that the copper product works better at higher concentration and at higher temperature, as would be expected. It should be noted that the copper treatments were refreshed every 3 days for the first 9 days, and then every 4 to 5 days thereafter. Copper refreshes are necessary to maintain the intended treatment concentration, because aqueous copper declines over time as biological organisms such as algae and the mussels pick up and sequester copper in their cells. The copper results show that there would be a number of potentially effective treatment options over different concentrations and different temperatures for United. The potassium chloride results were a bit more variable. Again, that could be because of that recovery step. Again, red arrows show 100% mortality across all 4 replicates, and gray arrows indicate near 100% mortality, but not complete mortality during the treatment period. However, the results clearly show that in the number of days tested, usually about 27 days, or up to 27 days, potassium chloride did not perform well at all at 10 degrees C in our Lake Piru water. The highest 2 concentrations performed okay at 17 degrees C, but never reached 100% mortality during the testing period, although both were at 98% mortality in 20 days. Potassium performed better at high temperature with a 95% kill in 11 days on the low concentration and 100% kill in 7 and 5 days for the medium and high temperatures, respectively. However, keep in mind that these concentrations were substantially higher than the 100 parts per million used at Millbrook Quarry. So we're testing 150, 200, and 250 parts per million. You can see that across the top. So based on the results, we would likely need to treat at about 200 parts per million, and Lake Piru is much greater volume than the quarry. On top of that, the Santa Clara watershed already struggles with exceeding chloride TMDLs for treated waste, from treated wastewater in upstream cities. So this makes adding large quantities of chloride to our watershed not a very attractive option for United. We did continue testing, and I don't have the results here today, for a period at low concentration for a longer amount of time, so about 2 months, just because potassium ions will stay in the water until they get diluted. So, so we have run that scenario, and we get very little mortality even after 2 months. So I'm still compiling that data, but I'll hopefully have it soon. So, therefore, we concluded that the chelated copper product we tested, EarthTech QZ, is probably the more cost-effective option for Lake Piru. However, given the designated critical habitat, the EPA has informed us that we need to pursue a special local need permit. During that process, the EPA will consult under the Endangered Species Act before issuing us the permit. So this wouldn't be the case in all reservoirs. It's more to do with the way our reservoir releases to that natural system. Previous testing has shown that EarthTech QZ formulation demonstrates low toxicity using lethal endpoints in Lake Piru water. However, both lethal and sublethal endpoints are important for Section 7 consultation. So we're having to look into both of those. So where do we go from here? We would likely want to treat at about 6,000 acre-feet so that we can still use our boat launch. So we're exploring a treatment around 200 parts per billion copper in the hottest time of year. However, we also have to balance the demands of our lake and our permits, and it would probably be a good idea to treat before any significant algae blooms occur, because the algae would also take up copper. So we may have to treat during a month that is not the warmest, so our data can help move us in the direction we need to go. Our current cost estimates for permitting and the application range from about $800,000 to about $2 million to do this project. We're currently in a proposal process with teams, and we will keep this community up to date as this project progresses. So just real quick, I just wanted to thank, we had a number of staff that helped with this project, and also David Hammond with Earth Science Laboratories, who provided the sample of EarthTech QZ and has given us on advice on the application, so the refreshes. And my contact information is here if anyone wants to follow up later. So just real quick, I saw that question come up. So the alkalinity in the hardness is very high, and I don't have the numbers right on the tip of my tongue, but we have very hard water, and our pH tends to be pretty high too, just because I saw that question pop up.
Thanks, Katherine. And I was going to post that question to you, but you beat me to it.
Well, I saw it pop up, so let's just address it now.
Thank you. And thanks for that presentation. So that's the only question we have right now, but folks may still continue to submit them as we go on. So if you can, stay on the line with us and we'll see if we get any more questions at the end.
Okay.
Our next presenter then is Diane Waller. Dr. Waller is a research fisheries biologist at the USGS Upper Midwest Environmental Sciences Center in La Crosse, Wisconsin. Her research focuses on evaluating effectiveness, selectivity, and non-target safety of management and control options for invasive species and dreissenid mussels in particular. So Diane, you should be all set to take over as presenter.
And can you hear me?
Yes, we can.
Okay.
I think we just lost you. Oh.
Did you lose?
There we go.
Okay. Well, carbon dioxide has been tested as a control tool for several different aquatic invasive species. In the 1990s, the Army Corps of Engineers actually looked at it to begin with to control macrofouling by dreissenids and the Asian clam on its infrastructure. And more recently, it's been tested against New Zealand mud snails. Our interest here started with its use to deter movement of invasive fish, including Asian carp. And carbon dioxide has some advantages over some other chemical control tools. It's environmentally neutral, it's pretty non-hazardous to work with. It doesn't persist after it's applied. You can off-gas it when you want the concentration removed from a body of water. It could also be pretty inexpensive if it's repurposed from an industrial source. We were especially interested in its toxicity in colder water temperatures. As we've just heard about, a lot of molluscicides are not very effective in colder water temperatures. When you put carbon dioxide in water, it has two major effects for aquatic organisms. It reacts to form carbonic acid, so it lowers the pH. And one effect of this on dreissenids is from the drop in pH. Claudia has reported that the chronic threshold for adults is around 6.5. For villagers, it's 6.9, and settlement can even be prevented at a pH of around 7. Secondly, because carbon dioxide has greater solubility than oxygen, when we infuse it into water, it drives off some of the oxygen and can cause hypoxia. So this is another component of stress for mussels. But the responses that we observe for mussels in carbon dioxide also suggest that it has some other physiological and neurological effects, as I'll show, that can increase its toxicity just beyond the effects on pH and hypoxia. So our objectives were to first determine what mortality we could achieve in carbon dioxide concentrations over exposures that ranged from 24 to 96 hours across a range of temperatures from about 4 degrees up to 20 degrees. We also wanted to look at some of the sublethal effects that could be taken advantage of in controlling zebra mussels, including a narcotizing response and its effects on their attachment. And lastly, we wanted to compare the responses between zebra mussels and native mussels. So native mussels were chosen as our non-target group for several reasons. First, dreissenids have adversely affected native mussels more than any other faunal group. They occupy the same habitats and are often the substrate for dreissenids. So they're going to be in the same place as dreissenid mussels and can't move out of the control area when an application is applied. This is our test system. We actually ran flow-through tests in a diluter system. In the picture that you see here, the CO2 tanks at the front of the photo, we just run an air line from there up into the first chamber of the diluter. Then the concentration of CO2 gets diluted by about 20% in each subsequent chamber. Down below you see our test tanks. We had 4 replicates of each concentration. So in these trials, we looked at a range of 5 CO2 concentrations and then a control. And because of temperature differences, we didn't get exactly the same CO2 concentration range in those 3 test temperatures. So on the graph here, the 4-degree trial is shown on the blue dots, the 12 in the black, and the red is the 20-degree. So just notice that our concentration at 4 degrees was lower than that at the 2 higher temperatures. The area in blue is where that concentration range overlapped for all 3 temperatures. So that's what most of the results are going to focus on, is mortality and attachment and so forth in that common range. I also just want to point out our exposure durations were every 24 hours, except at 12 degrees we didn't have a 72-hour exposure. These are our test animals. The zebra mussels came from a lake in Minnesota. Before each trial, we cut the Bissell threads of each mussel and then placed them onto tiles. If they didn't reattach, we didn't use them in the test. You can see them there on the left-hand photo. So a tile of 25 mussels was removed from each test tank at the 24-hour intervals. We then placed them in untreated water and then assess their mortality after a 7-day post-exposure period. The other responses that we measured included the number of mussels that were gaping or narcotized and attachment. So we actually wanted to look at the difference between the effect that CO2 had on the physical attachment of the Bissell plaque, which you see at the yellow arrows there, versus the effect that CO2 had on the ability of mussels to make Bissell threads. So in all but one group, the mussels were placed into the test tanks already attached to the tile. And then we counted the number that remained attached at the end of the exposure. So that was basically assessing just their ability to stay attached during exposure. But in a second group, the threads were cut near the ventral shell margin, and then we put them on the substrates and then into the test tanks. At the end of the 96-hour exposure, we then counted how many had been able to reform new Bissell threads. On the right-hand side of the screen, you see our non-target native mussels. Just because of availability, we tested 2 different species. Fat muckets were tested at 12 degrees and then pocketbooks at 4 and 20. These are both related Lanceolus species. They were obtained from the culture facilities at the Genoa National Fish Hatchery. All were about 6 months of age. They were tested simultaneously in the same tanks with the zebra mussels, and we assessed similar response variables, mortality, their bearing behavior, and also their ability to make Bissell threads. So this is what mussels look like on that CO2, similar to what you saw, their response in potassium chloride. The carbon dioxide causes them to gape, the foot extends, and they become narcotized. So we looked at the appearance or occurrence of this gaping behavior at the 3 different temperatures over those 24-hour exposure increments. So on the top graph here, we're looking at the response at 4 degrees. The red is 24 hours, blue is 48, then our yellow triangle is 72, and the black diamond is 96 hours of exposure. So here at 4 degrees, there seems to be a definite dose response. The higher the concentration, the more gaping that we saw, so that's not surprising. And then also at 4 degrees, the longer you leave them in, the more gaping occurs. Except for here at the higher concentration at 4 degrees, just a lot of overlap. So once we got above a certain concentration, it didn't seem to matter. They were gaping at 24 hours. On the next 2 graphs, we're looking at similar data at 12 degrees and 20 degrees. There's really less of a concentration effect here once you get above about 120 microatmospheres of carbon dioxide. Pretty consistent narcotizing behavior within 24 hours across all of those concentrations. Also, now if we compare 4 degrees to 20 degrees at the same concentration, there's really not much difference. Again, within 24 hours, regardless of the temperature, we got some pretty significant gaping occurring. And I want to also mention that these mussels do look dead, and if you're just going by gaping behavior, you far overestimate the mortality. So we found that we really did have to have a post-exposure period. We used 7 days in order to get an adequate assessment of mortality. So here's our mortality data to begin with, 20 degrees and 12 degrees, and now our, again, the red circles are 24 hours, blue is 48, the yellow 72, and the black is 96. So starting with 20 degrees, and the 24-hour exposure just was not long enough at the concentrations we tested to get 100% mortality. At 48 hours, also the only complete mortality we had was at the very high concentration. However, at 72 hours and then up to 96, we got pretty we had 100% mortality that occurred right along about 120 microatmospheres of carbon dioxide. Comparing at 12 degrees, again, 24 hours was not enough until you got way out here and still not complete mortality. 48 hours also was not quite enough to achieve complete mortality. But what was encouraging is if you expose them for 96 hours across even our lower concentration range, now we're starting to get between 90 and 100% mortality. So this graph is a little bit different. It's just looking at the 96-hour exposure, so our maximum exposure time, all 3 temperatures. So now I've included the 4-degree data. I just want to point out that at 4 degrees, we did not get 100% mortality at any of the concentrations. But again, we didn't achieve very high concentrations at 4 degrees either. And this is really to show the comparison of our percent mortality at comparable concentrations between 12 and 20 degrees. So there wasn't a huge amount of difference here between those two temperatures. And on this next graph, so here we're starting to put together a bit of a regression to estimate how much time you need to expose them to the CO2 at different water temperatures. So we chose a pretty moderate concentration here, 110 microliters, so that's a big number. It's produces a pH of about 6.15 in the water. So at 20 degrees, it's going to take about 96 hours, about 4.5 days. At 12 degrees, 152 hours. And again, these are trials that we just completed and actual hours that it took to complete that or achieve complete mortality. The last number here, this trial, we've just rerun at 4 degrees, so this number is not hard and solid yet, but it looks like it's going to take about 10 days at this concentration of CO2 to produce 100% mortality at 4 degrees. So next, to look at some of those sublethal responses of zebra mussels and carbon dioxide. Remember, I mentioned that in one group, we cut the Bissell threads before we put them in the carbon dioxide and then looked to see how many had formed Bissell threads. There's no graph of that because none of them were able to make a Bissell thread in the CO2 at even the lowest concentration. The graph that is shown here indicates the number that remained attached after just 24 hours of exposure. And this is kind of our, excuse me, common concentration for 4, 12, and 20 degrees. And what you'll see here is that this concentration, about 50%, had lost attachment. And I just want to point out that we didn't count the number of Bissell threads. We just counted yes or no, they were or weren't attached. So even at cold water temperatures, at lower concentrations, we can get a pretty good reduction in attachment. And honestly, it wouldn't take much force of water to have removed any of these that remained attached to the tiles. The other thing that's interesting here is that in colder water, at 4 degrees, there were fewer attached than there were at the higher temperature, and I suspect that's because they're just at the higher temperatures more actively able to make more Bissell threads than they are in the colder water. So the most surprising result of this study was of the native mussels. So they were exposed to the maximum 96 hours. Many of them after exposure looked dead. As you see here, the one that's circled in yellow, gaping, the foot is hanging out. But when we put them in untreated water for a week during that post-exposure period, the mussels that were in the 12 and the 4 degree trials had 100% survival. So this was very surprising that they were able to withstand those levels of CO2. However, at 20 degrees, we did get some mortality. At our highest concentrations that you see circled here, the 3 red boxes represent the mortalities that we had in these higher concentrations, and overall there was average mortality there of about 80%. There were a couple other mortalities at 20 degrees too, but they were not related to the treatment. Also notice here the black dots that extend out to the higher concentration. This was in the 12 degree trial. We had no mortality of mussels at 12 degrees, even though they were exposed to a higher concentration. So we're not sure if this was a difference in the condition of the mussels between the two temperature trials. In fact, these that were exposed to 12 degrees were fat muckets. The mussels exposed to 20 degrees were pocketbooks, so there might have been some species difference there. It's very possible, though, the lower water temperatures make them less susceptible to the CO2. So the pictures here show what we observed in tanks of native mussels. In the control tank, you see nothing because they are all buried underneath the sediment. In the picture here on the right, you see all the mussels have come out and are laying on the surface. So this is a response that native mussels have to the carbon dioxide as they unbury and then oftentimes gape or extend the foot. So to quantify this unburying behavior, the graph on the right shows in light blue at the different concentrations, the percent that were unburied after 96 hours. And you can see a dose response here. The higher the concentration, more of them unburied, so between 40 and about up to 100% of them unburied. However, when we put them in clean water, within a week's time, most of them had buried once more, and our number then dropped from 10 to 30%. So this was in the 12-degree trial. On this next slide, we're seeing really a difference in the response of the native mussels to CO2 at the different water temperatures. So our extreme here of 20 degrees versus 4. So at 20 degrees, as you'd expect, they were more active. We had a much greater response of them to come up out of the substrate. So up to 100% of them, again, were unburied. During the recovery period, though, fewer of them were able to rebury, so they didn't seem to recover as well at that higher temperature. This concentration I want to mention, these mussels all lived, they just didn't seem to be recovering as well. On the other hand, in colder water, this is typically a trigger for native mussels to begin burying. And so you can see the CO2 had much less effect on them. Most of them remained buried, even at the higher concentration. And the recovery period here was just a day later. The majority of them, if they did come up, had reburied. So the asterisks mean 100% of them were buried. We simply didn't see them in the colder water. So these results seem to suggest that it would really be safer for native mussels to be applying CO2 in colder water. So in conclusion, it looks like carbon dioxide could be effectively applied to kill zebra mussels. We just would have to, of course, adjust the dose and duration of exposure for water temperature. And I want to mention, the amount of free CO2 is also going to be very dependent on water chemistry. But it looks like it could be a viable tool for use in the fall, even into the winter, to remove dreissenids when other molluscicides might not be as effective. And as I mentioned, it also could be a safer time of the year to be treating areas with carbon dioxide, as a lot of native mussels would be buried. We could be using carbon dioxide to reduce or prevent attachment of dreissenids to substrates, and here we could use low concentrations, shorter periods of exposure. In this case, they could be used perhaps to remove dreissenids from high-value habitat as well as infrastructure. And something that we're especially interested in looking at is taking advantage of the narcotizing effect of carbon dioxide to use it as a pre-treatment. So perhaps causing them to gape, and then hitting them with molluscicide at a lower concentration to be more effective for killing them. So with that, I'd like to thank the Genoa National Fish Hatchery for supplying us with native mussels, and our funding was from the Great Lakes Restoration Initiative and USGS. So with that, I'll take questions if there are any, or turn it back to you.
Thank you, Diane. We do have one question. Do you have any cost estimates for what it would take to reach the killing thresholds in a lake?
For carbon dioxide, is that question?
Yes.
So not at this time, but this summer we're going to actually be doing some field application, not in a lake, but in a lock system in the Mississippi, and I think that'll really help us start narrowing in on some of the cost of it and the feasibility of applying it on a large scale. And I think part of that cost really depends on your source of CO2. So if it could be repurposed from an industrial source, I think that could reduce the cost significantly.
Thanks. And just as a reminder to our participants, you can type in any questions you have for Diane or for Katherine or Jim, for any of our presenters today, into the chat box if you have any questions. But that does conclude our presentations for today. So thank you again to Jim and Diane and Katherine. I don't see any questions coming in right now, but I want to give folks another minute or two if they're still typing. So go ahead.
This is Katherine Ayres. I went and grabbed some of our numbers to answer the earlier question. Our pH ranges from about 8.3 to about 8.7. It changes throughout the year. And our hardness, I have written down here, and I think this is right, is about 229 to 498 milligrams per liter as calcium carbonate. And I don't have the alkalinity right in front of me, but it's also tends to be quite high.
Thank you. While we give folks another minute to see if they have any questions, Katherine, Jim, or Diane, if you have questions for one another or anything that you didn't get a chance to say or forgot to say during your presentation that you'd like to add, you can go ahead and do that now as well. We do have a question that was just submitted, and this is for all three of you, Jim, Diane, and Katherine, for the different methods that you looked at. Do you have any information on veliger mortality from your research?
We have not yet evaluated veligers in the CO2. I think the assumption is that the adults will be more tolerant, so we were starting with them first.
Likewise, the same with the work we did. The adults were going to be the hardest life stage to kill, so that's what we went after.
And I would say, likewise, it's harder to do the veliger tests than the adults. So we just set up our lab, and we're going to be set up in a way to be able to do the veliger testing now. So hopefully we can do that soon.
I will add, we're hoping that we get some funding to do some veliger and settlement work in the field with Earth Tech. That's pending. We don't know if it's going to get funded, but it's looking promising at this point. So there might be something later on.
I think there is a published study on potassium chloride against veligers that I've seen.
Yeah, that's correct. There is. It's kind of old.
Yeah.
It's from Diane's work earlier.
Yeah, it's old.
We can, even though it is a bit older, we can make sure that that paper is available on our website with the rest of the recording materials. It might already be listed there, but we can cross-link it to the information for this webinar. Diane, I have another question for you. For the CO2 testing, did you remove mussel byssal threads? And yeah, so the question is, would CO2, if released in a water body, cause the byssal threads to degrade?
So what it looks like is that it loosens the plaque, which adheres them to the substrate. And it's possible too that the mussels themselves are in the CO2. I think that's one effect, is physically causing the plaque to dissolve, but it does look like they are actively releasing from the plaque as well. So I think there's a couple things that happen.
Thank you, Diane. We have another question here about during exposure time, was there any evaluation of predation on native species?
Is the question about like fish preying on zebra mussels or on the mussels?
Yes.
Yeah, we did not evaluate predation.
Katherine, have you evaluated predation in any of your studies?
Before I came to United, there was a test run of basically fish. I believe it was fish in cages under our docks, but I was told that it wasn't very successful, and that a lot of the fish got out of the traps, and so it may not be the best study to use.
Okay.
It could use further evaluation, but I don't think they saw a lot of predation. During exposure, I don't know. We haven't done that.
Thank you.
I guess during, yeah, okay.
I think that is all the questions we have. I just want to give folks one more minute in case they're still typing. But again, if any of our presenters, if you have anything you wanted to add before we wrap up today, please feel free to do so.
I might add, so with the copper, we did do a test where we didn't do a refresh, so we just added the copper and let it run. That definitely was not as successful at killing mussels as doing the refresh. So if you think of that in like a lake-wide treatment, you're going to have to bump up your copper concentrations, at least in the beginning, as they decline. So that's important to keep in mind, I think.
Yeah, I would speak to that with the carbon dioxide, but I think because of its solubility, when we put it into the colder water, it actually stayed there without, we retained it in solution for a lot longer period of time. So even though it seems like you'd need more of it in cold water, once you infused it in there, it stays if you don't actively off-gas it. As opposed to at higher temperatures, you're more likely going to have to continue to infuse it.
All right, well, thank you for that additional information. I'm not seeing any other questions come in, so I think we are going to wrap up for today. I want to thank all of our presenters and all of our participants again. And as a reminder, a recording of this webinar and related information will be posted on the Invasive Mussel Collaborative website in the next day or two. And if you have any additional follow-up questions or comments, please feel free to contact us at the Great Lakes Commission or via the collaborative website, and we will do our best to answer those for you. So thank you very much. Bye, everyone.
The part I'm not like that it's going to